first. The derivative of 4 to the negative x. So what is d dx of 4 to the negative x? Go ahead.
1 over...
Well, not 1 over, careful, that's for the...
Isn't it negative 4?
What happens to every exponential? Every exponential comes back.
You drop...
There's got to be a 4 to the negative x sitting in this thing, right? Every exponential function comes back. There may be a little more pieces to put onto it, but it's coming back. So I'm going to write 4 to the negative x. That has to be there, okay?
It would be negative 4x squared. Or minus.
Oh, okay, because there's like a...
So this comes back, right? But I need to compensate and give it the natural log of its base. So there's got to be an ln4 sitting here as well. Remember that? The lnb?
Why are we using ln now?
That's the formula for the exponential function derivative.
Oh, okay.
It has a factor of ln base on it. But wait, it was a negative x exponent. This is not just x. So this is a chain rule. I've got to multiply by the derivative of inner function. What's the derivative of negative x?
X1.
Negative 1.
Negative 1.
Keep guessing. You'll eventually get it. So it's negative natural log of 4 times 4 to the negative x is our derivative. For that little piece there, that's that piece. Now just put it all together, right? So you have 4 to the negative x cos x plus sine x, negative ln 4 to the negative x. They both have, meaning both terms, have 4 to the negative x. You should factor that off. So you have 4 to the negative x cos x minus natural log of 4 times sine x. There's our derivative. Okay?
Why just power?
It's not a power. It's an exponential function. And that is the difference between these two cases here. X to the third is a power function. The exponent, or the power, is constant, and the base is variable. Here, the base is constant, and the exponent is variable. These are the difference between these two functions. And we're going to have something in a second. It's going to be both variable. Here we have a tower function in a moment. We'll see how to deal with that. Yeah.
Can you explain the derivative of 4 to the negative x again?
Yeah. So the basic process was first use the exponential rule, which is natural log of base times original. Okay. Natural log of base times original for exponential. But the original had a function inside of it, a simple function, a negative x function, not just x, right? It's negative x. So I have to use the chain rule and multiply by the derivative of negative x, which is the negative 1, to finish off the derivative. Okay, so now we should be able to do this one, right? It's another product rule, no big deal. So first, x cubed times the derivative of the second. What's the derivative of the second? Carver, give it to me. What's the derivative of the second?
X.
No. What's the derivative of this thing? Come on! Ah!
X ln.
What is it?
Is it x ln 3?
No.
Is it ln 3 to the x?
Yeah. ln of base times original. Boom. That's first times derivative of second. Now we need second times derivative of the first. You guys got that too easy, so I'll do it. 3x squared. Okay. There's our derivative. But now we should factor out whatever we can. Clean it up, because you're going to have to in chapter 4 anyway for tons of problems, I hope. Equals, so they both have a 3 to the x, and they both have an x squared. So we'll take both of those out. So x squared, 3 to the x, and left inside the parentheses is ln 3 times the leftover x here, ln 3. I'm going to write it like that, so it does not look like it's ln of 3x, which it is not. The x is not inside the logarithm. This is just a constant, right? It's like 5x here. This is one big constant times x, plus 3. There's a bracket there. Is that okay? I think it's right. So,
Where's the x squared on the first part?
there's an x cubed. There's an x squared. So they both have x squareds. So that's why this term still has an x and this one doesn't. Right? That x times this is the x cubed. Okay, so now let's pretend we were in chapter 4 for one quick minute, or we had a question like, we want to know where the derivative is 0. Okay? This problem's going to come up a lot. I mentioned it the other day as well. 0. You want to know where this function possibly has maxes or mins, right? Where the slope is 0. The slope is horizontal, right? That's a possible max or min. So now you have this that equal to 0. In its factored form, you have something to do. Again, right? You have an implication that either x squared equals 0, or 3 to the x equals 0, or ln of 3 times x plus 3 equals 0. Agreed? Just those three factors that equal 0. So what is the answer to x squared equals 0? I got it. X is 0. All right? What is the answer to 3 to the x equals 0? This is the important one. Impossible. Good answer. Red herring. I should have written it red. Red herring. 3 to the x is never going to be 0, right? We said before, it only puts out positive values, right? Exponential, only positives. So anytime you have an exponential set equal to 0, it's a false clue. False clue. Right? So that's never going to happen. E to the x, 1/2 to the x, 5 to the x. Anytime you get exponential equal to 0, you're going to have them. Always realize there's nothing to do with it. Okay? So forget that. You can solve this one very easily. It's just a linear function, right? Slope x plus y-intercept. Okay? So we'll just solve it. So x equals -3 on ln of 3. Agreed? So that will be the basic setup you'll have in chapter 4. You need to find maxes and mins and things like that. You'll take a derivative set equal to 0, and you want it factored. You want to be able to clean it up algebraically, right? Make sure you have the facility to do that. Otherwise, there's just nowhere to go with those problems later on. All right, so that was our derivative. Now we're going to move on to a slightly more complicated type of function called a tower function, and see how to use the derivatives we just talked about to handle that case. So it's like I just described. For example, x cubed is a power function. The base is variable and power is constant. Okay? And you would differentiate with a power rule. That's what power rule is for, those cases. So what if you have something slightly different? In case we mentioned a second ago, 3 to the x. They have them combined together with that product. No good reason. So 3 to the x, what do you call this? You call it an exponential function. So the focus is on the variable being the exponent. Exponential function. Base constant, switches the roles, and power or exponent variable. And you know what to do with that now, right? ln of base times the original function. That's how you differentiate it, right? Now I want a tower function. So that's going to be f of x raised to the g of x. Okay? Tower function. Base variable, power variable, or exponent variable. Okay? They're both variable. Neither one of these rules, not the power and not the exponential derivative rules, are going to suffice for this case. Okay? We're going to use a slightly different type.